So yesterday we saw a few things, a few observational results, and I hope I convinced you that we have quite some solid evidence that we do see correlations between different galaxy properties. There's the main sequence of star-forming galaxies, galaxies that do have a very specific values of star formation rate at fixed stellar mass. We know that there are galaxies that are above the main sequence. We heard earlier today about starbursts and trying to move this galaxy up, and we know that there are galaxies below, galaxies that are quiescent or on the way to quiescence. So we left yesterday with this set of questions, and today I'd like to address. The first one is about the meaning of the main sequence. All right, so what does it mean that most of the star-forming galaxies in the universe across time tend to follow this correlation between stellar masses and formation rate? So I took this piece from the introduction of the very next paper by deviating and deviating, and it's in the introduction. So I think it just summarizes some salient points that are interesting. And let's go through them, starting from the yellow part. Maybe at this point it's a little bit redundant, but if most of the galaxies are in the main sequence from most of the cosmic time, then it just means that quite a lot of the star formation rate happens there, and the stellar mass is still there. So just to give you this more of a cosmological perspective, here you have the function of redshift at time, the evolution of the cosmic star formation density, which increases from high redshift. It peaks around redshift 1 to 3, and then increases. If you integrate the star formation rate, then that's the history of formation of stars in galaxies, so you can actually compute how many stars. And this is then the density of the stellar mass. And I think this is the rescaling between the integrating the star formation rate as a function of time with what is actually measured. And that's because not all the stars that you form remain in forms of stars. In galaxies, you have stars that explode and disappear, so you lose them. And you have material that is also ejected out of stars and returned into the ISM. So this returning factor is somewhere between 40–60%, depending on the item. This is the H1, so the neutral hydrogen. We didn't talk a lot about this. Let's focus mostly on this H2, which is fuel for star formation. And if it's true that you form stars out of this collective gas, then maybe it's not totally surprising that they have the same shape. But please remember how hard it is to estimate this quantity. We saw yesterday a series of craters. And it should not be taken for granted that you can actually measure H2 at such a high pressure. It's still a pretty complicated task. Okay, so most of the stars are formed in the main sequence. I think that probably at this point is the most common interpretation of the existence of the sequence is that, well, if most of the galaxies are growing along the main sequence, meaning that they keep forming stars depending on how much stellar mass you have, then there should be some sort of ordering. And this is despite what we heard this morning with all those things that are merging together at some point in time. Still, the underlying growth is rather regular. It's rather secular, especially again if it's doing a galaxy tend to grow on the sequence. Here, this is a plot from a paper by Lucis and I think Jeremy is also the author here. So if you start somewhere at high redshift, somewhere on the existence of the main sequence, I think it's seated at redshift 5, and you assume that this relation here, the stellar mass transformation rate, exists as a function of time. You have to choose your favorite characterization. Maybe there's some bending here. Then you can actually construct how the galaxies are evolving as a function of time. And then if you keep growing on the main sequence, then you do see this sort of evolution of the function. So again, probably the most common or the surprising point is that galaxies are growing somehow self-consistently in a very secular and smooth way, and that's what the main sequence is the reflection. Not only that, but if you assume that galaxies are growing indeed on the main sequence, you naturally have a certain specific shape of the star formation history. So for each, if you start at the very beginning, as we said, you see somehow the galaxy at some stellar mass here, and you just follow it as a function of time, then the natural outcome is a star formation history, which is the star formation rate as a function of time, that has some sort of rise and then decline. So that's just out of the assumption that the galaxies are growing on the correlation. And what I want to say, okay, these are different lines here, just depending on a series of corrections, most notably, again, how much mass loss you have. Not all the stars you born remain stars for a very long time, return function. But again, in general, the shape is that you have something that increases and that increases. And actually, this shape is also pretty much consistent with what you would determine on a cosmic average sense with those plots that I was showing you before. Probably star formation density has to be that shape if you have some sort of star formation histories that this one. And if you remember, when you start estimating stellar masses, star formation rates, and various properties from the SCD modeling, one of the ingredients is exactly assuming the star formation history or composite star populations. So one very common assumption is something called a delayed exponential or an exponential, otherwise an exponential decline in star formation history, which basically assumes some burst at some point and then an exponential decline. And actually, the exponential decline is consistent with what we would expect from integrating, again, growth of galaxies along the main sequence. Not only that, but now we start connecting a little bit more to a cosmological perspective, which is this green part here. There's much interest in the relation between stellar mass and star formation rate, or specific star formation rate of galaxies, because of the correlation that one could establish between the growth of galaxies, which is again the specific star formation rate over stellar mass. It just tells you how quickly the galaxy is growing in mass, with the accretion of dark matter on your halos. So this is what your dark matter accretion would predict, and this is instead star formation. The specific star formation rate, and you see that they actually trace each other pretty well. I'm going to come back to this in a second. And just for reference, this is taken from this seminal paper by Lilly that is actually trying to put all the main sequence and a series of autoscaling equations in a more general framework, which is what is called a gas regulator model. So first approximation, then we can try to understand this one here, because when the baryons end up in halos, basically tracing how dark matter is also ending up in halos. And surprisingly, maybe not, the evolution is a function of time. So basically, this is the normalization of your main sequence that goes like 1 plus z to the power 2 to 3. It's actually pretty similar to the one that you could also analytically derive for dark matter halos. So this goes by the idea again that the way the material is falling into halos and then reaching galaxies is just consistent between dark matter and the baryons. And then the last point, but I think this is pretty much what I was saying. By your dark matter accretion in IZ, then it means that you have more gas that is accreting onto the halos and higher star formation rate. And that's also pretty much resembles the shapes of the integrated star formation rate density and molecular gas density, which is this one here. So it's not surprising that you have more gas, then that's why you have mostly star formation rate that increases and peaks at the same, roughly the same magnitude. That's again because you form stars out of gas. And this one is roughly following through typical accretion of dark matter halos. The final point, which I'll just show you here for reference, is the exact same plot I was showing you yesterday. This is one of the versions of the main sequence of redshift 0 with your star galaxies here, quiescent galaxies down here in 2 different clouds. This is very massive, very few galaxies in between, and this is known as galaxies. Well, this is just because defining the framework of the main sequence allows you to determine what is an outlier with respect to this relation. So you have outliers below, and you have outliers here. The stars that I was mentioning this morning. So this is in general why the main sequence framework is important in some general terms, and you see that there's really quite some connection with what happens behind the scenes to dark matter evolution. This is another piece from another paper from Kepler and Academy. And again, about the meaning of the main sequence, not only the correlation is there as a function of redshift, then pretty much the same slope. But if you remember, there's also a rather small effect. And that's, again, going, at least in the main interpretation of this correlation, it's going to support the fact that basically galaxies are growing somehow in a quasi-steady fashion. Evolution is not purely and highly stochastic, the process of star formation. So this is what is mentioned here. So main sequence galaxies can be seen as your prototypical star-forming objects at any shift. And actually, you can try to make some mathematical sense out of this by a series of assumptions, which are encoded in this series of very nice papers. Nicolas Boucher proposed one. This is this Lily paper that I was mentioning before. Plus, these are analytical prescriptions, but of course, then you also have simulations, and that's one of the two things that trying to be bridged together. And this is, let's say, a graphical representation of how this the evolution of star forming galaxies works. So again, basically, there are a series of observational facts and theoretical assumptions, very well established. So how does a gas work? What do you need to make a gas work? Well, you need some gas that flows in. Keep in mind that when you have gas flowing into onto dark matter halos, you have some gas that ends up in halo and some gas that ends up towards the galaxy. When the gas reaches the galaxy, then you have some star formation. So this is the parameter that enters the sequence. Some stars remain in the galaxy, lonely stars. Some gas that is given back immediately to the ISM. And the idea here is that this level is self-regulated. And if you put in gas, depending on how fast that is separated to stars, you might have an increase of the overall gas reservoirs, which is followed then by the increase of star formation rate. When you start running out of gas core, the gas is transformed into stars faster than how much gas or how fast the gas is replenished, then this level goes down. And this is again a self-regulated process. Of course, when you have star formation, then you do have some outflows. You have super rejection here, so some gas can be expelled. Well, some of the gas will remain within the halo, so at that point, it's just, again, some sort of circulations in here. It's not going to be the same sort of gas that you have that comes from a cosmic web. This is somehow pristine. This is, let's say, hydrogen, some helium, and some metals. While as soon as you switch on star formation, you produce metals that are immediately released in the ISM or expelled and then reaccreted. In some cases, you do have outflows that can actually escape the potential well of the galaxy, and then you do have simply gas that is leaving the system. And this is metal-rich gas. So if you're looking, for example, at the metallicity in a galaxy, that's very sensitive to this sort of mechanism. Because when you form stars, you're basically forming stars out of, well, in the beginning, pristine gas, and then you immediately start enriching the ISM. If you have very metal-rich outflows that leave the gas, then your metallicity goes down. So the metallicity is a very good indicator of what's going on in the galaxy. It's basically a logbook where all the major events of the life of the galaxy are recorded. On top of that, you might have supermassive holes at the center that are also growing. I'm not going to touch upon that, but there's also that elements in the system. And this can actually be put into some equations. Basically, there's a continuity equation between the gas transformation into stars with some return factor. You need to know what is this mass loading factor of the outflow, so how much gas you're losing, if it's metal rich or not. And basically, you need this from your dark matter simulations or dark matter analytical prescriptions that says that, again, you have more gas that flows in depending on how much dark matter accretion you have. But this can be in some sort of equilibrium, and it has been remarkably successful in predicting the existence of a main sequence, in predicting the metallicity of galaxies, what is called the mass metallicity relation. Maybe you heard about fundamental mass metallicity relation, which is putting together stellar masses, metallicities, and star formation rates, and a series of other observable relations. And again, the basic idea is that galaxies somehow grow in this self-regulated system where depending on how much gas you have in and how much and how fast it is transforming to stars, well, then you do have an increase of your star formation rate from very high redshift to the peak. Then something happens here. I'm going to show you in a second what. And then if you cut this part, then of course you start running out of gas if you keep forming stars. And that's why your global star formation rate is a function of time goes down again. What do I mean with gas inflow? This is instead a simulation. This is from Schmidt-Kennicutt in 2009 paper. The accretion of gas can happen in different ways onto the halos, but basically what simulation has been consistently predicting since quite some years now is that there's a regime where the gas can actually flow into the halos in the form of this, what is called the cosmological flow. So this is cold gas, relatively cold gas, that can penetrate deep into the halo here represented by this circle and reach the galaxy. And this cold gas will feed then the star formation rate as a function of time. So this is seen in observations. This is just a projection then in the halo versus redshift space. So for low mass halos, this is standard as well. So everything here below, basically at any redshift, you can keep accreting cold gas. So that term that is bringing gas inside your galaxies is basically there all the time. So you do have gas replenishment, and this is what keeps your star forming galaxies active. But then there is something that happens above this threshold, and in principle, the halo becomes at some point so massive that all the gas that falls in is adiabatically shocked to very high temperatures. So you end up having very warm gas, which you might detect in X-rays. And actually, if you look at redshift 0, let's say your typical cluster masses, 10 to the 14, 10 to the 15, well, most of the gas that you have in these halos is emitting X-rays. It's pretty warm. But there's a regime in between these two, below and above the sensitive one threshold, where you can have actually a mix, and you have this cosmological cold flow that can actually penetrate cold down to the bottom of the potential wave. And here, this is just an extrapolation. If you take the observed cluster redshift 0, these are some simulations. These are instead like just extrapolation of how the typical halo grows as a function of time. And this is what you would call this. These are observations, these blue and red points. These are what you would call protoclusters of galaxies, meaning it's stuff that will end up being a cluster redshift 0, but at higher redshift, of course, might be below the typical threshold which is applied a cluster. And you see that actually this might be like perfect locations to look for this cosmological fault flows because they're very massive. So the dark matter accretion scales as a function of the halo mass. The higher the halo mass, the more you accrete. But then there are redshift which is high enough where you can actually find still cold flows in the very warm halos that instead you're drawing out of the channel shock heat. And yeah, so this is like a preferential location to look for this cold flows that have been looked for a pretty long time. It's a pretty hard business, but I think that now there are some pretty good candidates of direct detections of these cold flows going towards massive clusters or protoclusters. This is a product group, redshift 3-ish. So just to give you an idea, this is roughly close to the transition here. It is spectroscopically confirmed. We know that there are galaxies in here. There's a group of few galaxies and some that are very star forming. So we need to kind of know that they need to have some gas replenishment to be there. And then we look for line malformation. And this is the structure that you have there. And you do see this morphological, this morphology with extended filaments that go out this way. You also do have some information about kinematics. It's a bit of a tricky business because Lyman alpha is a resonant line. So the shape of the spectrum is not necessarily directed with the kinematics of a gas because you have resonant effects. But you can try to include that. And actually, this is a pretty good example. Again, this is not part of what I have been doing in collaboration with Emanuele Dati, but there are other examples. It's a very nice paper that was published in Science a couple of years ago showing a structure which is 1 megaparsec long emitting in lamina, but in a protoclastic redshift grid. So I think that we're kind of now reaching a point where this long search cosmological flows can actually be probably directly investigated despite a lot of caveats in the environment. So this is what I mean by gas accretion. Keep in mind that here the galaxies are much smaller. This is the proper size, which is roughly the virial radius of this, the virial diameter. It's comparable with the size of the halo. Your galaxies are much smaller and they sit somewhere here in a very gas-rich environment, which is what you would expect from gas that is flowing in. The other side of the relation we saw yesterday, so we said stellar mass versus star formation rate is the main sequence, that star formation rate is fueled by gas masses. And so we introduced the Schmidt-Kennicutt relation, which Jeremy recalled this morning. So how much gas you have correlates with how much star formation rate you have, especially when you look at surface density. And this is another variation of an analytical model, which is actually trying to model all these correlations in some sort of consistent way. It has been published several years ago by Genzel and then updated several times. This is the latest version, to my knowledge. The depletion time scale, remember, is the time that you need to deplete your gas. So how fast basically your gas is converted into stars, or how efficiently you convert a particle of gas into new stars. It's the efficiency is the opposite of this inverse 1 over the depletion times. Keep in mind that it's not a true efficiency, it doesn't have the units of an inverse time. So it's a bit of a jargon definition here. But this is basically how quickly your gas is transformed into stars. And you see that there's a dependence on the redshift and on the distance of the main sequence. Just means that if you have starbursts going upwards on the main sequence, this number goes up. This is the star formation rate compared to the star formation rates of your typical galaxy sequence. And this is like dependent on the stellar mass. Again, that's because the main sequence is not maybe exactly linear, so you might have some sort of slip with stellar mass. But what is interesting here is that the main dependence is on the redshift. And then there's a secondary dependence on the distance from the main sequence, meaning that starbursts are more efficient at forming a star. The depletion times are shorter, which is what Jeremy was mentioning this morning. But there's basically no other dependency. This is on stellar mass, but they tried with sizes, they tried with environment. And this is pretty good at describing the average properties of galaxies on the main sequence, Kennicutt, as a function of time. So again, the global rates of gas accretion, so how the gas ends up in the halo, so it's basically encapsulated on the correlation of the dependence on redshift, in this part here. There's an increase in efficiency when you have gas-rich unstable disk. This happens especially in high redshift. The more gas-rich you are, the more turbulent you should be. We'll come back to that later. There's again some peak of efficiency. So where do you form the stars at the highest possible efficiency in what kind of halos? And okay, maybe not surprisingly, you see that this is the same halo threshold that I was showing you before. So this 10 to the 12 dark matter virial mass. And then it decreases at lower masses, and it decreases at higher masses. And if you're familiar with stellar mass functions and halo mass functions, you must have seen this halo mass over stellar mass or the halo mass star formation rate ratios as a function of halo mass, for example. And we know that, at least from a theoretical perspective, we do need to have some feedback from something within the galaxies to avoid to have too many stars. And at low mass, for low mass galaxies, we think this is supernova. So you form stars in a low mass galaxy, which has a potential well which is pretty shallow. So you let some stars explode, and these winds can escape the potential well more easily than if you have a very massive object, because the massive object with deeper potential well retains the gas. While at the high mass, we think it might be AGN. AGN are pretty effective at launching hot flows that are much faster than supernova. And actually, this is the kind of recipe that when you have a simulation, you have to put in with your subgrid physics to reproduce stellar mass functions. Below small scale efficiency, this is the 1% that Jeremy was mentioning this morning, is again, the star formation rate is a function of gas mass normalized by the critical time. And it's remarkably similar across this galaxy, 1%. And it also, you can extrapolate this and try to reproduce the global content, again, of the molecular gas density in the universe. And it does reproduce the same shape, something that increases from high redshift to redshift 1 to 3 and then decreases again. So this is just to give you another brief perspective. This is purely analytical, and in this case, it's actually based on out-of-field correlations, what we see, and it's remarkably successful. And the theoretical background here is something like what I showed you before, this gas-regulated model, this model, the galaxy self-regulating star formation based on how much gas you get and how quickly you convert it into stars and how much gas you eject. Okay, so this is something about the general evolution of the function of time. You have a good reproduction of the slope. You have a good constraint with respect to the cosmic star formation rate density, and so the global view of how the universe is stars. But there's more to the sequence, which is the scatter. We said that the small scatter should actually be indicative of the fact that the typical galaxy grows in roughly the same way, at least in this general interpretation of the frame. Well, okay, this brings us to something a little bit deeper, maybe, and might actually question a little bit the meaning of the main sequence that I explained so far. So the main sequence scatter here, again, I'm quoting from this paper from Kepler and Takela, is directly related to the variability of the star formation history, and hence encodes physical mechanisms acting in different times. So what is this telling us? It's just telling us that the scatter is interesting. It's just telling us how the typical growth of galaxies is actually, well, how diverse you have, how diverse the paths are to form galaxies on the main sequence. And you might think at least to two possible scenarios. The first one is that you have short-term fluctuation. So galaxies are growing on the main sequence and they just fluctuate somehow along the main sequence. Maybe at some point they scatter out, it could have a big merger, maybe not. We heard that there are different conditions to have galaxies going up. But that's roughly what this first scenario predicts. So short time fluctuations, let's say some 100 million years, you lose memory of what happens on the time scale longer, and then you keep growing. The alternative instead is that you have long-term fluctuations. Then the star formation in galaxies is actually not related to what changes the star formation in time scales, which could be feedback, let's say, supernova going up or having some AGN at some point there. But it's something which is more fundamental and related to how the galaxies are growing on a longer time scale, which actually might have to do with what happens in the growth of dark matter. So this is just two examples of the first category and the second category. Again, the short time fluctuations are basically related to the physics of what happens connected with the star formation of galaxies. So feedback, outflow, you can have some minor mergers, or maybe a major merger if you shoot a dynamic sequence, or fluctuation, you can get accretion. While long-term time variations are mostly related to the formation times and the halo mass at which the galaxy formation was seeded at the very beginning. So let me just zoom in. This is the first, this is one version. It's from Takela, the work based on some simulations. Actually, the same set of simulations that I was showing you before with the flows of gas going in. And the idea here is that you start at some point with some blue galaxies that is forming whatever number of stars you expect. Zero here is on the main sequence. This is distance from the main sequence. So this plus minus 0.3x is roughly the scatter of the main sequence. Your starburst would be up here, your coalescing galaxy would be here below. And again, these things are very gas rich, they're turbulent, and they keep accreting gas because we are in those regimes where the gas can actually penetrate the halos and make it to the galaxies. What happens here in this view is that since these galaxies are so rich and turbulent and stable, you could have some dynamical perturbation. It doesn't have to be necessarily a big merge. It could be like a minor accretion event, or maybe some lump of gas, which is a little bit more massive. Well, then you start triggering this bundling of gas that we heard this morning underneath towards the center. So the outcome that you expect is that the galaxy shrinks. It gets smaller. You have most of the gas which is funneled towards the center, it gets rich. And then you trigger a burst, which follows the fact that you put a lot of gas and you compress it in small regions, higher efficiencies. Well, at this point, then the replenishment of gas is slower than the typical depletion time. So how quickly you're converting into stars. So you start running out of gas and you move down the main sequencing. And actually, this thing can happen several times as long as these conditions are met. So the depletion times here get shorter or longer than the accretion. So if the accretion is shorter, you replenish the galaxy. If you form stars faster, you consume the gas and you replenish it. And you keep going until at some point something happens. And this is what they highlight here. This is the halo mass below or above that threshold that was shown. If you're below, you can easily accrete gas. If you're above, well, that becomes pretty hard. So in this last moment here, you reach a situation where the halo is pretty massive and you're at pretty low redshift. So you stop accreting gas that easily. And the outcome is that, well, no more gas. Your galaxy starts to quench. You shut down at some pace. And the outcome then here is that your galaxy drops below the main sequence and you keep the same sort of shape that you had the last moment where you were forming stars. So this would be a natural way to predict massive quiescence small galaxies or duration, let's say, 2-ish. And then since we're astronomers, we start getting some fancy names. This is blue nuggets. This is called the red nuggets. That's just there. On the other hand, this is instead from a simulation. This is from Eagle. This is trying to figure out that the have a galaxy on the main sequence at some redshift, in this case low redshift, and you try to trace it as a function of time. Well, it turns out that if you have short time scale variations around the main sequence, basically you end up raising the signal around this zero value. Again, this is the distance from the main sequence. This is a function of time. What they find in this paper by Metti and Shoya is that actually, if you are above the main sequence, you've been above the main sequence for most of your history of formation. And if you're below, you tend to be below. So this is going against what we were saying before, that we have fluctuations around the main sequence, but most likely, depending on where you started, you stay above or below, and the main sequence is just a reflection of something which is above and something which is below, and you just happen to find them at the same time of the correlation. By the way, the final conclusion here, they were trying to figure out if it's short time scale or long time dominating the scatter sequence, and they conclude that it's both. And it's roughly 0.2, 0.3x from one side, 0.2, 0.3x for the other components, you square them up, and then you add them, and you get your points in scatter sequence. So this is still pretty much open as a question, but it can be pretty interesting because it subtends two different interpretations of the main sequence. This is something fundamental. Galaxies grow along the main sequence, while this one might just be a reflection of diversity of star histories, and that's pretty interesting as an argument to take care of. Is there a way to test it? Yeah, sorry, this is also like a natural consequence. Second, you need something to take your galaxy off the main sequence, quenching some event. Maybe linked to the fact that you can't gas accretion, maybe because you expel the gas, like that. Well, this one would just be a natural evolution of increase and decrease in the star formation history that would just explain as well your cosmological star formation. Is there a way to test this? I mean, if you can look at the temporal variation of star formation rates in galaxies, then maybe we can say that this is short time scale variations or long time scale variation. And we saw that we do have a list here of different tracers that are sensitive to different time scales. And in principle, if you compare what happens on 100 million time scale with, for example, what you can write on a chatbot, let's say, which is on 10 million time scales, then if you do see some systematic differences in there, you can try to figure out if galaxies are actually oscillating on the same sequence or something the two are coupled and they change in the same way. The problem here, people tried. The problem here is that dust complicates a lot of things. Especially, when you observe a galaxy, you do have observed dust-obscured UV and dust-obscured HR. And the way you correct them to the intrinsic properties, which is what you need to the right side of the release, then that depends on your dust collections, and that's a tricky business. Two things can be corrected the same way. You can have higher attenuation in clouds rather than stars, and so on and so forth. And this might really easily wash out any signal. Okay, so this was about the meaning of the main sequence, the general interpretation with some caveats about what is underlying the main sequence. Is really fundamental. Well, we think it generally is, but there are attempts to do to come up with other alternative explanations, and the scatter actually might contain enough information to let us decide at some point, even if it's still pretty hard. This is about instead what happens outside the sequence. Do galaxies grow different? That's because I said that so far, those nice analytical models, the top models, simulations, they're able to persistently reproduce main sequence and how galaxies grow there. But we do know that there are outliers. There are few, they contribute somehow to some calculation rate, but they're there, so we have to figure out what happens. And again, here we're focusing on stars. So those few percent galaxies, this is, as we showed this morning, remarkably consistent, a few percent. And they contribute to some percent of the total star. In the local universe, you saw already this picture, just rotated in a different way. This is another one. It's actually for you, thank you. Basically, all the local star bursts, strongly stopping galaxies out of gas-rich mergers. They're very bright in the infrared. They're very dusty. So that's why it's easy to detect them. And the idea is that you might have some equilibrium that's broken. For example, you have merging galaxies that have a burst for a few, let's say, maybe 100 million years or something like that. And you do have a lot of density there. Okay, we heard how this could work in a much more detailed way. But what happens at high redshift? Are these things still just colliding galaxies that are very rich? Well, probably some are colliding galaxies, but there are indications that the picture might just be a little bit more complex. So this is a collection of what you see in dust emission. So this is the emission of dust in galaxies that are pretty bright. These are called sub-millimeter galaxies. That's because they were initially identified as bright dots in the sub-millimeter that have 50 micron per spray. Observed, at higher shift with the scuba instruments. And now this is a version from a very powerful interpreter called ALMA. ALMA is a great advantage that allows you to look at the structure of galaxies. So this is basically what in the optical would be a points per function. This is like the smaller size, that you can probe. And you see that these things look actually pretty extended, so nothing crazy compact like those dusty cores that you would expect when you merge galaxies together. But they're also, it's pretty extended. And not only that, there's now indications that these things are not trendless. So if you look at how the gas is distributed in this galaxy and how it's moving, it's actually remarkably regular. So we're still debating at the moment what is the goal of mergers. Is it true that mergers are the only way we have to form stars? Is it true that all stars are mergers? Well, probably the second one. We know that it's not the case. We heard this morning that to have an advancement of star formation rate, especially in high redshift, you do need some special conditions. It's also pretty hard. These are gas rich and they're not stable. So as I mentioned before, you just need a little bit of a dynamical perturbation, and that gas tends to go towards the center and form these compact cores. which could actually be a very good way to form quantum formation. These are those red nuggets that the simulation is predicting. But this is some recent positive finding that's just mentioned. So not only this thing is extended over several kiloparsecs, but if you look at how the gas is moving within these galaxies, it's remarkably cold on a dynamical sense. So let me just guide you through this. This is redshift, and this is the V over sigma. Right? This is rotational velocity over velocity dispersion. So if you have something which is dominated by rotation, this number is high. If you have something that is pressure supported by movements, then this number goes down. So a lower redshift, redshift 0, this is based on H1, I think. So very extended disks. We know it's the typical rotation curves that you see when you're doing your astronomy class, and it goes up, it flattens out. And this is measurements instead from ionized gas, on redshift 1 to 2, I think. And then you do have some higher measurements down here. The point is that recent observations of strongly star-forming galaxies, these are some of the most intensely star-forming galaxies that we know in high shift, and they're very well spectroscopically confirmed. They're lensed, so they're very bright, and they do reconstruct the dynamics on very small scales. Actually, they have pretty high V over sigma ratios, which is not what you would expect with the simulations, which tend to have this decrease. We heard this morning that the velocity dispersion tends to increase for very gas turbulent objects. And it's not what you would extrapolate based on observations of the atoms. Now, these are just a few, and we do need to fill in this gap. This is based on observations of the C+, so ionized carbon, which is a very bright line. It's great because it probes some colder phases of your ISM. What colder phase means probably some molecular phase, definitely neutral phase, which is definitely colder than the typical observations you can have with H alpha or oxygen-free, which is what we were limited to around redshift 1 to 3. Here, there's quite some more measurements. But now the point is trying to figure out what happens when we look at cold gas here. Why didn't we do that before? We do have ALMA, we can observe CO, which is basically the coldest phase that we can possibly observe. It is incredibly expensive. And that's because to do the proper kinematic decomposition, you do need very small beams, very small sets, let's say, in the optical generator, so that you can actually resolve the position and the movement of the gas, the cold gas. So hopefully we're going to have more results here. And here, actually, 4 to 5, there was a large ALMA program last summer with Crystal, which should add another 15 points of more typical main sequence galaxies here. So we can actually see the difference between SMGs and starburst and main sequence galaxies. So this is something very recent that was brought up by Francesco Maria and then a few other people. There are several papers by Lelli, Fraternali, and a few others. And now this is emerging as pretty solid evidence. If your starbursts are actually generated by mergers, then you would probably not expect to find a gorgeous lens and very extended disk, which is nicely rotating with very low velocity dispersion. But this remains to be seen. There are predictions from simulations that have disks that are other transient features. So you reform a disk out of accretion, but it disappears, and something which is then long and steady, so it forms a very hard. So the jury is still out. We'll see what's going to happen in the next few years. Something that I was asked about yesterday by one of you. What about this possibility? Starburst in the main sequence or on the main sequence. Well, if it happens, again, thanks to ALMA, which is a phenomenal instrument that allows you to look at the structure of the galaxy in instant. This is the distance from the main sequence again. So main sequence in blue, starburst above, and this is the same in the three panels. This is the depletion timescale again. So this is what you would predict based on the main sequence, this blue band. So again, starbursts are more efficient, so they have shorter depletion timescales up here, while on the main sequence you would expect this. This is the amount of gas, so gas fraction, which is increasing here as a function of distance from the main sequence, and this is the dust temperature, something that you can measure from your peripheral solutions. But there's a population of objects here which are on the main sequence. So technically, it's something that you would define a main sequence typical galaxy based on star formation rate and stellar mass. But if you look at their properties in terms of gas, these things are systematically gas poor. So their gas fraction is something like 20-30%. Their depletion times is very high. Sorry, they're very short. The efficiency is very high. You can understand, right? For the same amount of gas, they're very, very star forming, so the ratio is going down. And they're actually pretty warm in terms of the destination. So what are these things? Are they main sequence galaxies or part of scatter, or what happens? Maybe it's some effect of the variability within the main sequence, maybe not. There are different options, but something interesting here is that all these objects are remarkably small. They're common. So the surface density of these quantities, star formation and gas mass, as a function of the area projected, is going up pretty much. So the density is very high, and so the efficiency also is very high because it's number. So is this just some variability of the main sequence, something that maybe simulations predict, like I showed you before, or is something else? And are these galaxies just happen to be on the main sequence, or are they actually growing along the main sequence with constellations? And if they're actually not on the main sequence, but they're moving out of it, where are they going? Again, this is pretty recent work that we were talking about a few years ago. David does, and this is the work from Carlos Cascado. This is the work from the group I work with. And this is again the picture. One interesting thing of this scenario mentioned before is that you should find up here on the upper main sequence galaxies that are small. Okay, we do have galaxies that are small, like galaxies that are gas rich, while there's almost none found. And the galaxies that should be here below, there should be still substantially enriching gas, but most of these things are actually found to be gas poor. So probably this view of how things are going up and down is not a full description of what's going on, but it might just be that these objects, maybe due to some mergers, something that happened, we understand how they get compact. The gases can be brought towards the center, but they might actually be on their way down. So maybe they're on their way down from the main sequence, maybe they're on the way down from above the main sequence, but being very massive and living in halos that are like per cluster, probably they will not have enough gas accretion to sustain another episode of probation up. And what we see is just the final moments towards quiescence. So they're small, they're very star forming, they're gas poor. So it means that they're going to run out of gas pretty fast, and we will have some sort of quenching. This is just a possible explanation. There are ways probably to test it. We can see what are the properties of the gas in these objects. Are they looking like starburst galaxies? We heard yesterday the concept of spectral line energy distribution from the when we talked about the concerto. Is the spectral line energy distribution of these things more like the typical SMGs and starburst, or is it something that looks like a sequence? We don't know. So there's still quite some work left to be done, but this is just an application of things that have been emerging within the last few years, where I think the main sequence were a pretty solid framework to work with, but it gets richer and richer. So maybe there is something more going beyond that. And at some point you see if this will hold the test of time. Okay, the last part is going to be about what happens when galaxies form below the sequence, how do galaxies die, where death here just means stop forming stars, or stop forming stars at the rate you would expect for your typical stop forming galaxy on the main sequence. And back to this plot that I showed you yesterday. Well, we already have the spoilers, so I'm going to be completely new, but just to remind you, this is stellar mass, the massive galaxy on the right, and this is colors. So red is up and blue is down. And if you put all the galaxies together, this is from SDSS, which is 0, then you do find a saddle in between this red and blue clouds. Now we know that these are your typical main sequence galaxies, while these ones are red quiescent objects. But if you split them in terms of morphology, then you do have early type galaxies that are basically all up here, and very few that are bluish, while the late type has some sort of continuum distribution all the way up there. So even the concept of green valley objects and how the objects are transitioning from blue to red is it's depending on outer parameters. And this is the version split by the Halo mass. So now you see why this 10 to the 12 would actually be pretty interesting as a pressure. Above 10 to the 12, it's very hard to have gas going towards your galaxies. So you stop the gas accretion. Below, you do have some gas accretion. So you can't sustain the accretion. And this is actually zero. So you don't have that transitioning part of the parameter space where you might have flows going in. And in that sense, then, you can understand how these two populations are predicting or depicting two different kinds of transitions, slow and fast. Early type, they tend to transition fast, especially these massive things have been probably quite in the early type for quite some time. They're the first galaxies to quench. We have to find a quenching mechanism that might explain their shape, the fact that they live in massive halos, and the fact that they have pretty compact, at least in high rush. They grow up a little bit. Whatever is quenching at the moment is happening in, these blue objects here are probably just on the way to out quenching, but they do have some star formation probably supported by some gas accretion in this low masses. While here you see that all the objects that are transitioning, that are late type, are actually doing that in very massive levels. So here we have to figure out a way to retain the shape of the late type spirals, but to cut down their star formation. And now we probably have a good explanation, at least for low Russian, which is you just cut the accretion of gas onto the galaxy. You cut replenishments, the galaxy probably in some sort of self-regulated fashion fades out, and then you see the change of the colors from the pigment. By the way, this specific explanation, which actually might be related to some physical processes, maybe you've heard of ground pressure shifting or the interaction of something called galaxy resonance, something like that. It does work on scales that are typical of crucial clusters, and they're actually able to strip the gas, so you retain the shape. And if whatever star formation rate is ongoing keeps going, just reaches the metal enough to then match this population. It's a very nice paper by same group of these people. 2015. This is another version. This is exactly from this paper. This is just showing you that as a function of mass, the quiescent or the red fraction. So again, in this case, red means quiescent, blue means subatomic. You see that basically above a certain mass fraction, which is 10 to the 11, galaxies are always quiescent. It looks like if you reach them, there is something happens and you quench. While at lower masses, you get red only over dense environment. So this is where your cluster improves, probably would be. So this again might be related to the fact that you have very massive halos up here and very low mass halos here. So here you can keep forming stars, you have gas accreting. Here you don't. It's cut out of here. But the presence of a massive halo. Great. Ratio 0. Sorry, this is just again a representation of what I explained to, and it's exactly what it says. You have gas accretion on your spiral, the galaxy grows, probably somehow along the sequence. You cut the gas, the galaxy starts running out of it, and then it slowly transitions going down, and it maintains its shape. Great. We might also have some candidate physical mechanisms to explain this. While you have early type, here is associated with the merger elements. You do have coalescence between two elements. It's great because you can probably explain the final shape by relaxation plus gas piling towards the center, and then the galaxy suddenly drops down, and it ends up being an early, by 35 galaxy prototype. Great, can do that. This is again another version of why you have this threshold as well. This is in the original Bechtel paper. This is the typical growth of a halo mass that ends up being a group-like halo. And so if you're down here, you're accretion, here you don't, here probably you do have, but it works only in high rush. So what then if we look at galaxies around redshift 2-ish, where you should see all these different phases? Well, probably something works similarly to that. So this is back to color diagram, something that I showed yesterday at the beginning. So red quiescent galaxies are up here in this box, blue star-forming galaxies are down here, and actually this shape here is just due to dust. So if you have some star formation with some dust, your galaxy moves up this way, while if you go up here, then you're dead. Yes. And interestingly, you can still predict a couple of tracks, fast and slow. So a slow track would be something that is associated probably with broader galaxy properties. Maybe the environment is slowly grows, and then when you shut off the star formation, it goes down and goes up. While galaxies that end up being down here have a quench which is somehow faster. Faster means, let's say, 500,000, 1 billion years from. And actually, this last paper by Francesco here compares what happens in the color space, this is observed, with what happens in the stellar mass versus, this is the central density of stars. So basically, you have compact configuration, small galaxies, you have very high values here, and you see that the red quiescent type galaxies are at the very top. These are the smallest objects, the ones with the highest densities that you can find, while these are instead some blue extended objects. And you see that there are at least two tracks. First one that goes from small and compact, those blue nuggets, maybe they're small and something, and they turn out to be then early type quiescence, or something which instead goes slowly up. We just have to keep in mind a little caveat here, that is, we cannot really follow galaxy evolution as a function of time. You cannot track the same galaxy, see how it becomes smaller, how it quenches, and so on and so forth. So you have to mesh populations. And you do that in some sort of smart ways. You try to connect, for example, galaxies that have meaningful number densities. So naively, you would expect to need at least as many progenitors of your galaxy population as descendants, because otherwise you have follow-ons. There are different ways to do that, but this is just to say that there's something called progenitor models, which is inherent in our galaxy evolution models, especially for observations. You need to try to connect populations, and you cannot just follow the same galaxy. And the way you do this connection can be a bit problematic. And this is just a compilation of proposed mechanisms to quench your galaxies. This is from a paper by Bendy. You probably have a combination of these things. You have different processes that are going on, different mass regimes, probably different redshifts. Basically, you have two big families. One is you cut the gas accretion. This probably happens in any case, especially in low redshift and for massive halos. Or you have to get rid of the gas. We heard this morning an example of how you can quench without getting rid of the gas. So gas is there, but it's not transformed into stars. This is what we quenching. You have other versions here. You might have some heating from an AGN. The AGN actually might be able to remove the gas. Mergers, maybe they're just triggering the bursts, then you just simply eat all the gas by quantum stars. We still really don't know, especially at higher redshifts where you start seeing the first flights. So this is still pretty much discussed. But maybe there's a way to try to figure out things, which is, well, we know that stars are formed of gas, so why don't we look for gas in galaxies that recently died, or gas that died sometime. So this morning we heard that redshift 0. So here, there are galaxies that are quiescent, so they're not forming a lot of stars, but they do have some gas. So this is like a 1% gas fraction, and this is converted into dust. That's because, again, dust is tracing cold gas in galaxies. So you have this number right here. So this is what you expect in the local universe. Your typical main sequence galaxies follow this trend. But then you can start now looking for quiescent galaxies as a function of time and see how much dust or gas they have. It's very hard because they're faint. So people have been relying on two approaches. And so here you have two examples. People either stacked hundreds of quiescent galaxies trying to look for some signal. This is the work by Rafael and Yorgo Magnus. And you see that you find these points here from stack. So at quenching a redshifts 2, you have something which might add up to 5, 6, 7% of the stellar mass, which is still in gas. So this thing here, the quenching, would still retain quite some gas. So you would favor quenching processes that are not getting rid of all the gas to explain the quiescence. But other groups, like actually Whittaker here, has been using lensing. Gravitational lensing is great because it just allows you to go much, much deeper in short time space. For some quiescent galaxies, here you have control of the selection function. Here you just get whatever you get. And these are actually a little bit of a mixed bag in terms of especially stellar masses. And you see that you have some upper limits here that are much lower, like 1%. Now, this is what happened over the last few years. We still don't know if you do have all quiescent galaxies are retaining gas and dust at the end. You get rid of dust pretty easily. It's a little harder to get rid of gas. Maybe there's still some remaining star formation that is just slowly bringing you down here. These are just a handful of objects, like 7 or 8. This is stacking in one field. So there's a lot of work to be done, but this looks pretty promising. And if we are able actually to figure out if the average galaxy has very low gas content or high gas content at quenching, then this would help us figuring out what is killing galaxies. The last minute here is going to be about extremely high redshift. We now found 2 starbursts of quiescent galaxy redshift 4. So this is a big jump. Redshift 2, we kind of made it to be comparably reproduced by observation and by simulations models, but then just this nice paper by Karl Glazebrook in 2017 showing these gorgeous absorption lines in the galaxy redshift 3.7, and then other groups have been confirming more and more. I think that the current record is published in a couple of years ago, which is this redshift 4.01 post-Thomas. And obviously, at redshift 4, the universe was like 1.5 billion years old. So you cannot really have a slow quench. It has to be some complex. These things are massive, something like 10 to the 11. The point here is that we start finding so many of this that it's becoming uncomfortably to make for models and simulations. These things are massive. We have to figure out who are the progenitors of these objects, or to need enough of the progenitors and with the right properties. And we have to figure out if you need some sort of rapid growth, maybe through a merger, or maybe some more normal main sequence galaxy growth is sufficient. Keep in mind that main sequence normal growth at redshift 5 or 6 might need hundreds of solar masses per year and 10 to the 11 stellar masses, solar masses, which is typical stellar mass here. Just to give you an idea, this is a compilation by Yang and Lin. This is just counting these objects. This is counting quiescent objects as a function of redshift. So you have, these are the observed points, redshift 4 you have a few. These are what models and simulations predict. So you see there are models that fail also at lower redshift. This was the original illustrious one cosmological simulation. The updated version is the blue and the green ones. So you do see that you have different way of killing galaxies. And this is actually encoded in what you put in your subgroup physics in simulations. So you need some feedback from maybe stars exploding, the AGN. You need to get rid somehow of a gas and quench these objects in cosmological simulations. And this is where we're now stand. We're probing redshift 4-ish. And you see that, well, most of the models and simulations produce very few quiescent objects, even 0 over redshift 4. Some maybe produce a bit more, but then they undershoot it here. So, okay, what's going on? And the great thing is that now JWST is there, and this should be an obvious science case, because right now we're limited at redshift 4 by spectroscopic observations from the ground. The atmosphere just killed you. But JWST is not going to be found there, and it can go to lower places. I'm an observer, so at the beginning to be careful about observation bias. I showed you how models are not doing great, but I want to be fair, observations are not that consistent. This is the typical number that I just showed you before, number densities for quiescent objects at those high redshift. The paper I showed you before is these two lines, but this is a compilation of other people who tried, and this is what the simulations are predicting. And you see that between one estimate and the other, there is almost a factor of 10. So obviously, as observers, we also have to do better. And again, there's great hope that JWST is going to help us figuring that out. What I tried here is to show what happens when you try to connect two populations. This is the population of very star-forming galaxies, SMGs, with starburst objects, and higher redshift. So again, what I'm doing here, I'm just trying to count how many progenitors you might have and how many descendants you might have. So if you assume some sort of average number here, average number here, it turns out that you have very few SMGs compared to the number of quiescent objects. And in order to connect the two, you would have to assume quite some big correction factors. You should have to assume a duty cycle, which is a few million years. So actually, there might be a need to look for more typical galaxies, main sequence galaxies, that then turn out to be quiescent by order. Good news that there are some good candidates. These are called dropouts. Basically, you see them. You don't see them in HST bands, but then they pop up immediately in at long wavelengths. This is Spitzer, and then this is alpha. So it's clearly just the stuff. It was very hard to account for them before, but now we can, and which is obviously going to be even more. And so maybe these objects that are not your prototypical super bursty objects, but more like main sequence probably, they could be good progenitors. We have a lot of this in our fields. So this is still totally open, totally debated. Stay tuned in the next few years to figure it out. This is a standard evolution for massive quiescent objects. We saw basically how you would expect some strong merger versus formation. Something happens here in terms of quenching. This is associated with an AGN event, which is the favorite solution for simulations, but still see the remnant is a small compact red object. The later evolution, I didn't touch upon this, but they grow basically in size by incorporating smaller objects and depositing the stars in the outskirts, those odorous shells that we saw yesterday, but not a lot of this. Question is, this was from 2014. It was meant to explain the existence of quiescent galaxy emission 2. Now this thing is up here, direction 4. So does it still work or not? We figure out. Okay, this drives us to the last point about trying to put everything together. This is a nice, little bit artistic representation from this review here. It's a very good one. It's trying to look at all the scaling relations and try to present them and present all the interpretations of the main sequence and how galaxies grow, so on and so forth in a very nice way. So here is time, and this is various quantities that you see. So you have the growth of size. Galaxies become bigger and bigger as a function of time. You can see how the gas fraction is actually decreasing in galaxies. This is the typical star formation rate with that shape that we discussed. It has to increase and then exponentially decrease. Then if you integrate the blue one, you have the red one, which is how the stellar mass is assembled, the metallicity, and so on and so forth. And this is how galaxies would grow on the next series, assuming this scenario. And you see that you do expect some growth and then decrease, and maybe you do need something that kills the galaxy here, which is quenching. We saw different possibilities. Now, what is the meaning of existence of all these correlations? Are there correlations that are more fundamental than others? Can we come up with good models to represent how typical galaxies evolving? And I showed you some examples that even with analytical calculations, they're very successful at figuring out how galaxies are evolving. But of course, then you have outliers, and the more we look into the main sequence, Schmidt-Kennicutt and correlations, the more we find things that might not be consistent with this scenario. And I think the future is going to be there, trying to make some sense of what happens with the scatter of the main sequence, which has a lot of information included, and then try to understand what happens for starburst and quenching systems at the highest possible ratio. So I'll leave you with, yes, no, we don't have white slide. With this one, and I'm happy to hear any questions.
So thank you very much for this very nice presentation. Do we have any questions in the assembly? Okay, so I will start with one about the V sigma, V over sigma relation. Can you go back on the slide? That was a very, very interesting result. So we do able to get this one. So it's incredible that at high redshift you tend to have the same view of sigma than at low redshift, even higher maybe.
Yeah.
My first question is, what's the absolute value of circular velocity and sigma that you have? Are they similar to redshift 0 as well? Or?
So sigma is something like, I checked it this morning when we were showing the results. I think it's 20 to 30, something like that.
Okay, so it's a bit higher.
Yeah, it's not incredibly low.
So the sigma and the V are both higher by a factor 2 to 3,
Something like
redshift 0.
Yes. I can point you that in the example.
And what's your take on these values, where they come from, and why you don't see them in simulations?
I don't have a stake. I have it, and that's why I put it here, just to show you it's a lot yet to be discovered, something that Francesco is launched working actively on. And actually, it's pretty interesting, right? Because it's, you see all the models and simulations are going down. But there are new refined models that are trying to make sense of this. And there are these two explanations that we're trying to test now. And you can test them by seeing how many of this you have as a function of regression. Now, this is a kind of a sweet spot because it happens to be the right spot where to look for C+, and for less objects from a specific survey, which is the SPT survey. And it was great. But then what happens at the peak of the cosmological test is still pretty much unknown. There are a few galaxies where we can do that. And there are at least two explanations. One is that these things end up being here just because there's, as you also explained, some gas accretion distant form, or it's something which is long-lived. And you still do not have enough statistics to figure it out. So this is really like at the beginning. But it's interesting enough because, again, the ALMA telescope accepted a large program to go after 15 or something like that more of galaxies that are on the big sequence and try to populate the same redshift. So at the end, we're going to have like 20, 30 galaxies nicely spreading over our correlations and try to figure out if indeed this is a feature or not, and how it changes the function mass, gas content. So I don't have a very personal thought. Say here, I don't work directly with this, but I found it very fascinating and something that deviates from what we thought we could have seen. And it's recent, so there's a lot still left to do. That's the message.
Great, thanks. So any question? Yes.
Yes, I will try to solutions to cosmology, and my question is whether this main sequence can be used to test of cosmological models, something that we studied in different theories of gravity, or I don't know, question dark energy.
I don't know exactly about the main sequence itself, but there are probably some tests, especially on how many massive bands, for example, you can form in a specific redshift. The point there is that I guess that that's you will have some sort of dark matter mass function that you can produce with your favorite cosmological recipe. The problem here is that, of course, we observe variance. So there's always this trick in simulations and models that you have to go from dark matter to variance, and that heavily relies on scales that we cannot resolve. So there's a lot of stuff with physics that can change the results without changing anything about the cosmology. I would say that simulations now tend to be consistent in reproducing these correlations. They all tend to assume the same sort of lambda C and maybe whatever set of initial conditions. But I know there are some groups that are trying actually now to do some different, for example, different recipes for dark matter, having then some prescription for variance and see what happens. But I would say it's not my main area of research. I'm not sure how constraining it might be if we don't get the variance right first, I would say. But again, it's just my opinion.
So then this question about redshift 4 is, again, probably this discussion is within standard models, within the context of standard models, standard physics.
Yes, yeah, again, for example, the comparison that I'm showing between how many of these objects you have versus how many you would predict from simulations or models is, to my knowledge, I mean, you can look at the list here. You do have Illustris, Eagle, Simba. I think that these are like state-of-the-art cosmological simulations that they try to reproduce things at lower redshift, so they're benchmarked against whatever is stellar mass function and so on and so forth. And then you just see what happens at higher redshift, and you might fall short. But again, for example, if you just look in Illustris 1, TNG 100 here, so these are just two different versions of a simulation where they change their recipes for scientific physics. So basically, it's the feedback, for example, of AGNs and this kind of stuff. And you see that you tweak that, and the difference is dramatic between between this blue line here and the gray line here. So here they were just having a lot of problems in even matching redshift zero observations of how massive galaxies you have. Sorry. While you tweak that, and it's still like, say, black cosmology, maybe they updated with the business, and then you just push it up here. So there's still a lot of this sort of physics that you have to play with, and you cannot resolve, I think, for quite some time.
Thanks.
So any other questions? So I have another one on the variability of the scatter. So can you go back on the slide where you show the Eagle results?
Yes.
So I was a bit confused by that.
Yeah.
I think you just had to like the fork. Right. So here what you show is that when a galaxy at redshift at
Yeah, you can see this one is the two sets of observations. So the solid line is galaxies that are redshift zero, have a specific star formation which is above this threshold, and this is what is below this threshold, and then it's just tracing that. Yes. And I think I have another way of seeing that, which I didn't put in, which is this one. So this is the main sequence itself. This is redshift. And you can see how the trajectories are actually intercepting the main sequence of the function of time. But it doesn't mean that they go necessarily along the main sequence through this short time variability. But it's actually what's that their growth is basically how they're seeded. So in the end, it's the halo mass and how it grows which determines their long-term evolution. Actually, the two effects can be combined together. And the conclusion of the paper here is that they're almost equivalently important for what they conclude. So you still have some variability on short time scales, which you do expect. You do have supernova exploding. You do have some AGN that goes on and on with duty cycle. You have mergers, but there's also some effect on longer time scales. If you're in a massive halo, it's going to keep accreting gas more, and then it reaches the thresholds very massive earlier than you quench earlier. There's some sort of balance.
And so what's the main difference between the one that stays up and the one that stays below? Is it history or environmental?
Yeah, probably the two.
Those are the main factors.
I think that's the final explanation. I can double check the details, but I think that's what is encoded in this long-term variations.
But actually means, if you take the value that the scatter that is due to shorters back etc. is much less than 3x. Because in this scatter you already have
of course it's less than you would expect if it were completely due to that. But yeah, it's quadratic sum, so it is not that small.
Okay. Do you have any other question about galaxy evolution? It might be the last talk about galaxy evolution, right? Yes. Last chance. And what about the detection of the 3 planet elements you had with your paper manually? What redshift was that?
That's redshift 2.9.
Okay.
And it's basically the lower boundary that you have with the big IFUs. This is GEC.
It was Lyman alpha.
Yes, this is Lyman. This is basically just Lyman alpha emission. So hydrogen. The idea here is that the Lyman alpha is basically powered by cooling the vitamin. So hydrogen is just going and flowing in, and you actually can study the profiles and figure out what's going on. But the problem is that there's a lot of other ways to do it, science and ionize hydrogen. So you have to take care of those. But the energetics, the final budgets, you do need quite some. For example, AGN. There's a lot of luminosity here, so Goodbye.